In this module, we would be discussing the role of expectations, moments and moment generating functions. How do we first calculate these statistics and then solve few examples to get a more clear idea? Originally, the concept of a mathematical expectation arose in connection with games of chance and is calculated by multiplying the winning amount with the probability of winning. Recently, mathematical expectations have been playing a significant role in scientific decision making. In economics, when we have many alternatives, it is considered rational to choose that alternative which has the most promising mathematical expectation. That is the one that maximizes the expected profit, minimizes the expected cost, maximizes the consumer or producer surplus, and so on. The role of moments in statistics has always been very important. Moments have been used to give descriptions of probability distribution of functions of random variables. Moment generating functions also have great practical relevance, not only because they can be used to easily derive moments, but also because it can be used to determine a unique probability distribution. After studying this module, you shall be able to know what are the expected values of random variables and its properties, to define moments and moment generating functions, calculate the moments and moment generating functions of a random variable, identify and evaluate the different types of moments, analyze the role of moment generating function, to know the utility of a moment generating function to find the mean and variance of a random variable. First, we shall understand what is expectation. The expected value of a random variable is the arithmetic mean of that variable. Expected value is a weighted average of the possible values that x can take on, each value being weighted by the probability that x assumes it. Expectations is basically used to study the descriptive quantities of a data. The data can be discrete or continuous, and so the expectation also varies according to the type of data. Let x be a random variable. If the distribution of x is discrete, the expectation or expected value of x is defined to be Ex is equal to mu x, which is equal to sigma xp of x, where Ex is the expectation value of the discrete random variable x, small x is the value of the discrete random variable capital X, and p of small x is the probability mass function of capital X. For a continuous random variable x ranging over all the real numbers, the expectation is defined by Ex is equal to mu x, which is equal to integration from minus infinity to plus infinity of x function of x dx, where Ex is the expectation value of the continuous random variable x, small x is the value of the continuous random variable capital X, and fx is the probability density function. Properties of expectation. Following are the properties of expectation. First, linearity. The expected value of the product of a constant and the random variable is the value of the product of the constant and the expected value of the variable. Let small c be a constant and x, y are random variables. Then Ecx is equal to Cex. The expected value of the sum of the random variables is the sum of the expected values of the individual variables. Ex plus y is equal to Ex plus Ey. Constant. The expected value of a constant is the value of the constant itself. Let small c be a constant. Then Ec is equal to C. Product. The expected value of the product of the random variable is the product of the expected value of the variable. Let x and y be independent random variables. Then Exy is equal to Ex into Ey. Also, the variance of x is defined as the expectation of the random variable. X minus mu whole square. Thus, sigma squared x is equal to Ex minus mu x the whole squared, which is equal to Ex squared minus mu x squared, where sigma squared x is the variance of x, Ex squared is equal to sigma x squared px. Only when variance x is equal to 0, then Ex squared is equal to Ex the whole squared. Absolute convergence is required for uniqueness of the expected value. Moving on to the discussion of moments. Moments are the expected value of a power of the deviation of a random variable from a fixed value. So symbolically, MCN is equal to E x minus c raised to the power of n. Here M stands for moment, E is the expected value, x is the random value, n stands for the power or the nth moment, c is the fixed value from which deviation is taken. The moments of a distribution are a set of parameters that summarize it. Depending on the values of n and c, we can calculate various terms which are very essential in statistical economics. For example, when the value of c is 0, we are talking about raw moments. And further, if n is equal to 1, we are calculating mean of the distribution. Also, when c is equal to the expected value of the random variable, we are talking about central moments. And further, if n is equal to 2, we are calculating the variance of the random variable. Thus, mean and variance are functions of moments. The next section will discuss this in detail. Raw moments. When the deviation from the random value is 0, that is c is equal to 0, we are talking about raw moments. In general, the kth moment of a random variable x about the origin is defined by MOK is equal to EXK. That is, the kth moment of a random variable about the origin is the expected value of xk. The first raw moment, or simply the first moment about 0, is referred to as the distribution's mean. This is very simple to prove, since MO1 is equal to EX minus 0 raised to the power of 1, which is equal to EX. Similarly, extending further, MO2 is equal to EX squared divided by MOK equal to EX raised to the power of k. Central moments. The central moments are the kth moment about the mean, denoted by MUK, and can be written as E x minus mu raised to the power of k. Through central moments, we can calculate many important measures in statistics, which is explained below. First, the variance of the distribution denoted by sigma squared, or Vx, is same as m mu squared. Sigma squared is equal to mu squared, which is equal to Ex minus mu the whole squared. The third moment about the mean divided by the standard deviation raised to the power of 3 is used to construct a measure of skewness. Skewness is equal to third moment about the mean divided by sigma raised to the power of 3 by 2, which is equal to m cube mu divided by m squared mu raised to the power of 3 by 2, which is equal to Ex minus mu cube divided by sigma 3 by 2. Skewness describes whether the probability mass is more to the left or to the right of the mean, which is the symmetry, compared to a normal distribution. If the skewness is symmetric, then skewness is 0. The fourth moment about the mean divided by the square of the variance is used to construct a measure of kurtosis. M mu 4 divided by m mu squared the whole squared is equal to Ex minus mu raised to the power of 4 divided by Ex minus mu the whole squared. It measures the peakedness of the tail of symmetric distribution. Also, the first moment about the mean is always 0. That is, m mu 1 is equal to Ex minus mu raised to the power of 1, which is equal to Ex minus E mu, which is equal to mu minus mu equal to 0. Relationship between raw and central moments. The two definitions of moment, raw and central, are related. For example, we have already seen that the variance of x denoted by Vx can be computed as Vx is equal to Ex squared minus Ex the whole square. Thus, m squared mu is equal to m squared O minus m1 the whole square. Similar relationship can be found out between the higher moments by writing out the terms of the binomial expansion of x minus mu. Let us now discuss the moment generating function, or the MGF of x, which is defined by mxt is equal to E in bracket small e raised to the power of tx bracket closed, provided this expression is finite for t in the neighborhood of 0 and t is an auxiliary function. In other terms, the moment generating function can be interpreted as the expectation of the random variable tx. Also, mx0 always exists and is equal to 1. A key problem with moment generating functions is that moments and moment generating function may not exist, as the integrals need not converge absolutely. Using the following theorem, we can obtain or generate all the moments of x using the MGF. Theorem: E x raised to the power of r is equal to mxk into 0, which is equal to d raised to the power of r mxt divided by dtr divided by t, which is equal to 0. Proof: taking the power series expansion of Ex yields Exi is equal to 1 plus xt plus x squared t squared divided by 2 factorial plus x cubed t cubed divided by 3 factorial, etc. Taking the expectation of the above equation yields E bracket open ext, which is bracket shut, which is equal to 1 plus ext plus e x squared t squared divided by 2 factorial plus e x cubed t cubed divided by 3 factorial, etc., which is equal to ext, which is equal to 1 plus t ex plus t squared 2 factorial ex squared plus t cubed 3 factorial ex cubed, etc., which is equal to m ext, which is equal to 1 plus tmo1 plus t squared 2 factorial mo squared plus t3 3 factorial mo cube, etc. Thus, we can extract all the moments of the distribution from the MGF by applying the above theorem. That is, we can find the kth moment of x by taking the kth derivative of the moment generating function and setting t is equal to 0. Since expected value of xk is equal to dk mt divided by dtk, where you have t is equal to 0. This is because if we differentiate mt once, the only term that not multiplied by t or a power of t is mo raised to the power of 1. So dmt by dt divided by t is equal to 0, which is equal to mo1. Similarly, d squared mt divided by d2 squared divided by t is equal to 0, which is equal to mo squared. Generalizing, it is easy to show that to get the kth moment of a random variable x about the origin, we need to differentiate only its mgf k times with respect to t and then set t to 0. Thus, moment generating functions can sometimes make finding the mean and variance of a random variable simpler. Given a moment generating function exists for a random variable x, then first, the mean of x can be found by evaluating the first derivative of the moment generating function at t is equal to 0. That is, mu is equal to e x, which is equal to m0 raised to the power of 1. Second, the variance of x can be found by evaluating the first and second derivatives of the moment generating function at t is equal to 0. That is 2. Sigma squared is equal to ex squared is minus ex the whole squared, which is equal to d squared mt divided by d2 squared, where t is equal to 0, minus d1 mt divided by dt1, where t is equal to 0, the whole squared. Properties of moment generating functions. First, if x and y are two independent random variables, the MGF of their sum is the product of their MGFs. If the individual MGFs are mxt and myt respectively, the MGF of their sum is m x plus y raised to the power of t, which is equal to e multiplied by and bracket open e raised to the power of t x plus y bracket close, which is equal to e raised to the power of tx into e raised to the power of ty, which is equal to e capital bracket open small e raised to the power of tx into capital E small e raised to the power of ty from independence, which is equal to mxt into myt. If y is equal to a plus by is a linear transformation of x, then its MGF is myt is equal to e raised to the power of at mx bt. Since e raised to the power of ty is equal to e bracket open e t a plus bx bracket close is equal to capital E bracket open small e raised to the power of at into small e raised to the power of btx, which is equal to small e raised to the power of et capital E bracket open small e raised to the power of btx bracket closed, which is equal to e raised to the power of at mx bt. As a corollary, if mt is the mgf of a random variable x, the mgf of x minus mu is given by e raised to the power of minus mu t into mt. The moments about the origin of x minus mu are the moments about the mean of x. So to compute the kth moment about the mean for a random variable x, we can differentiate e raised to the power of minus mu t into mt k times with respect to t and set t equal to 0. Thirdly, if two random variables x and y have the same cumulative distribution function, then they have the same moments. That is, fxx is equal to fyx for all x, then e bracket open x raised to the power of k is equal to e y raised to the power of k for all k. Corollary, but the inverse is not necessarily true. That is, the same moments does not necessarily have the same cumulative distribution function. So it is possible that for ex raised to the power of k is equal to eyk all k, but fxx is not equal to fyx for some x. Fourthly, if two distributions have the same moment generating function, then they have the same cumulative distribution function. That is for all values of t. mxt is equal to myt. Then fxx is equal to fyx. For all values of x, or equivalently, x and y have the same distribution. This statement is not equivalent to the statement if two distributions have the same moments, then they have the same cumulative distribution function. The log normal distribution is an example of when this occurs. Also, it is sometimes simpler to work with the logarithm of the moment generating function, which is also called the cumulant generating function and is defined by rt is equivalent to log mt, or r epsilon t is equal to m epsilon t divided by mt, or r double epsilon t is equal to mt into m epsilon t minus m epsilon t the whole square divided by mt the whole square. But mo is equal to 1, which is 1. So mu is equal to m comma 0, which is equal to r comma 0, which is then that sigma squared is equal to mo minus m dash o the whole squared, which is equal to ro. Example, given fx is equal to lambda e raised to the power of minus lambda x for x greater than 0, calculate 1 the mean, 2 the variance. mxt is equal to e small e raised to the power of tx, which is equal to integral sign 0 to minus infinity ext fx dx. From 5.2, since x is a continuous random variable, mt integration 0 to infinity e raised to the power of xt fx dx, which is equal to integration 0 to infinity ext lambda e raised to the power of minus lambda x dx, which is equal to lambda integration 0 to infinity e raised to the power of 1 minus lambda x dx is equal to lambda e raised to the power of t minus lambda x divided by t minus lambda 0 to infinity s, which is equal to lambda divided by lambda minus t for all lambda greater than t, which is equal to ex is equal to dgt divided by dt for t is equal to 0, which is equal to lambda divided by lambda minus t squared for t equal to 0, which is equal to 1 over lambda. Ex squared is equal to d squared gt divided by dt squared, which is equal to lambda 2 into lambda minus t divided by lambda minus t raised to the power of 4, which is equal to 2 lambda squared divided by lambda raised to the power of 4, which is equal to 2 over lambda squared. Therefore, variance x is equal to e x squared minus Ex the whole squared, which is equal to 2 divided by lambda squared minus 1 by lambda the whole squared, which is equal to 1 over lambda squared. Let us now summarize what we have learnt in this module. First, the expected value of a random variable is the arithmetic mean of that variable. The expected values Ex, Ex squared, Ex cube, right up to Ex raised to the power of r are also called moments about the origin. The moment generating function can be interpreted as the expectation of the random variable e raised to the power of tx. A moment generating function can not only be used to find moments of a random variable, it can also be used to identify which probability mass function a random variable follows.